3, 2, 1. Oh.
This is my upgraded air cannon. In the last video I built version 1 of this cannon, but it used a ball valve, which limited its performance a lot because it had an inconsistent and slow opening time. That's why I used a large solenoid valve for this cannon to address those issues and improve the cannon performance by a lot. In a pilot operated solenoid valve, electric current energizes a coil to create a magnetic field. This lifts an internal pin, opening a small orifice that drops the internal pressure and triggers the main valve mechanism to open. I selected this 1-inch valve to achieve high flow rates and fast response times despite its indirect internal path. This one has 1-inch BSP pipe threads on it. Because of the indirect path, I had to take the flow coefficient into account, so I updated the mathematical model of the system, which I made in the last video. I also upgraded the optimization software, but more on that later. First, to find out the current that the valve is gonna use, I first measured the resistance of the coil. And this coil has a resistance of 6 ohms. Because the valve works on 12 volts, I could then calculate the current using that equation, and it turned out to be exactly 2 amperes. To power the valve, I chose this RC plane battery, which claims to have a maximum continuous discharge of 80C, which corresponds to around 176 amperes, which should be more than enough. To measure the tank pressure in the first cannon, I used a bike pump, which turned out to be really inaccurate, so in this one I'll be using this hydraulic pressure sensor, which is rated for up to 150 psi, which should be more than enough for our purposes. So I designed and 3D printed this 1-inch BSP pipe thread to bottle thread adapter, which the sensor can be screwed onto. I printed it out of 100% thin film PETG at high temperature, which should make it airtight and durable. And it turned out quite good. However, because of my printer settings, it turned out a bit messy, but good nonetheless, and it was just easy to file away the lumps of plastic for a smooth enough surface. I attached the adapter to the air tank using some Teflon tape to seal the gaps between the threads. I had to use quite a lot of it, because of the imperfections and whatnot in the 3D printed threads. To attach and seal the pressure sensor to the adapter part, I used this O-ring, which goes onto there like that, and screws onto here like this. It was a bit tight, so I had to use this tool to tighten it properly. I would have used a rubber gasket had I had one, but I didn't have any, so I had to improvise by using an O-ring. Then I used some 2-part epoxy to attach the bicycle valve thing to the bottle, just to make sure it's fully sealed. For sealing the gap between the 3D printed adapter part and the solenoid valve, I also used an O-ring, which I stretched around the threads, and then it just screws onto the solenoid valve like that. Next, I designed and 3D printed a case for all of the electronics that are going to control the pressure sensor. After printing it, it had some thin plastic hairs and stuff on it, which I was easily able to clean up by just using this lighter to burn them off quickly. For the electronics, I'll be using this Arduino Nano version 3 microcontroller, which will be powered by 3 AA batteries in a case, which means that it'll be easy to replace them once they are depleted. I'll also be using this step-up module to keep the input voltage for the Arduino at exactly 5 volts. This tiny LCD screen will show the pressure reading. Then I soldered everything together and used this crimping tool to put some DuPont connectors onto the wires. After that, I 3D printed the lid for the case. It also turned out quite nice, and it didn't take long to clean it up. The power switch fits into that hole and snaps into place. I used some hot glue to quickly glue the LCD screen to the underside of the lid, and it looks really nice. To secure all of the solder connections and prevent any accidental short circuits, I covered the connections with some epoxy. After installing all of the electronics into the case, it was time for me to make the code for the Arduino. The code's purpose is to read the sensor data, after which it displays the gauge pressure in real time on the LCD monitor. The pressure sensor I'm using was designed to work linearly because of the piezoelectric phenomenon, where a crystal structure changes its resistance depending on the pressure exerted onto it. So the code interprets the pressure reading based on a linear relationship between voltage and pressure. The batteries snap into there easily like that, and then the lid is screwed on with 4 small screws. And I think it turned out really nice and quite professional looking. And when I flip the power switch on, it successfully turns on. And off. First, I decided to test it by putting some pressure into the air tank and seeing if it leaks or not, and if the pressure sensor works correctly and shows the correct pressure reading. And it seemed to work just as expected. But I needed to have an easier way to activate the solenoid valve, so I decided to add the trigger switch to it, which would release the valve once I switch it on to the on position. Like this. To measure the precise velocity of the projectiles, I'll be using this ballistic chronograph. In the first air cannon video, I tried measuring the velocity using my camera, but the velocity of the projectiles was far too fast for my camera, even in slow motion. The ballistic chronograph is able to capture the velocity of projectiles even at extreme speeds because of how it works. It uses these 2 light gates, which the projectile flies through and interrupts, and based on the difference in time when they are interrupted, the chronograph calculates the velocity of the projectile using the simple equation that velocity is distance traveled divided by time. Here you can see how it works when I throw a roll of electrical tape through it. The projectiles can also be quite big, as long as they fit through the light gates. Next, for attaching the barrel to the valve, I 3D printed this PSP 1-inch pipe thread to PVC pipe adapter out of the same 100% infill PETG. I also glued it with some 2-part epoxy to the PVC pipe for a proper seal. In the last video, I used the same PVC pipe, but a short barrel and a long one. In this video, I also decided to use this 28mm inner diameter PVC pipe. For this larger PVC pipe, I also 3D printed a large adapter, which I also glued onto the larger barrel using the same 2-part epoxy glue. To make the barrel look cool, I wrapped it in some black vinyl covering. Then the barrel just screws onto the solenoid valve like that, and is also sealed using an O-ring. Because the barrel screws onto the valve, it means that it is detachable, which means that I can change the barrel easily, and the O-ring always provides a proper seal. Then I attached everything to the air tank with some electrical tape, as it was the easiest temporary solution. I had to use a different battery, as I accidentally fully depleted and destroyed that other one. After the entire air cannon was finished and fully ready to test, I also needed some projectiles for it. In the last video, I 3D printed these cylindrical projectiles out of solid TPU, but there were 2 major problems. First, they were leaky around the edges, and secondly, they tumbled after leaving the barrel, which resulted in really bad performance. So, for these tests, I made the projectiles out of paper, which I made into cones, and precisely measured and cut into the shape of the barrel to ensure there wasn't gonna be any leakage. To ensure that these projectiles will travel straight and not tumble, I decided to add some hot glue inside of them as nose weight, which should provide plenty of stability. I also made a couple more of them. An interesting thing about this type of projectile is that even if there's a slight gap between the projectile and the wall of the barrel, The pressurized air behind it will essentially seal it, because of the paper slightly conforming due to pressure. Then I did a quick test to see if my model is even remotely accurate. When I compared the measured velocity to what the model predicted, I noticed that it was overestimating it by a lot. I then realized that it wasn't taking into account the gas friction or the inertia of the air, so I had to fix that by adding the Fano gas friction and Lagrange gas inertia approximation to the model. After that, the result lined up much better with what the model had predicted, and it was within one standard deviation. In the updated UI, I added the option to input the temperature in Celsius instead of Kelvin, and also randomize it as well as other parameters, such as valve opening time and gas friction. I also added some other tabs to the program. In this tab, I can evaluate the performance of the system with those parameters I've inputted, and based on that, calculate how fast the projectile will be moving at a certain pressure. In this tab, I can input the measured velocities and what pressures I used, and compare how accurate the model is. To test the cannon, I'll be using the 2.5 meter long barrel, and the plan is to try and validate the mathematical model of the system by comparing it to 20 different points of data, which I'll collect from doing 5 launches per pressure at 2, 3, 4 and 5 bar. The barrel is easy to reload each time, as it just screws on and off within seconds. First, I'll start at 2 bar and then go higher after 5 launches each time.
3, 2, 1.
This is a launch at 5 bar, and here you can see just how much recoil this thing has.
3, 2, 1. Oh. 3, 2, 1. Oh.
So all of this got stuck right here. Which is quite good because they're just paper cones. After running the tests, the results were surprisingly consistent. Out of 20 launches, only one didn't register because the chronograph threw an error. After plugging the data into the software, I noticed that the model seemed to overestimate performance by a lot at low pressures and underestimate it at high pressures. I then realized that because it's this kind of solenoid valve, the valve opening time isn't constant and it depends on the pressure differential, meaning that at higher pressure, the valve opening time is much faster than at low pressure to a certain point until the flow becomes saturated. I realized that by adjusting the valve opening time parameter, I could find out the valve system response time at each pressure and interpolate that to be used as the valve parameter. So I added some boxes where I could input those values, which is essentially calibrating the model for this valve and barrel diameter based on the experimental data. I could automate it, but this was just a quick solution. The model is now basically 99% accurate for this system, and the validation was successful. Now I could make the accurate optimization curve. From this we can see that the barrel we used, which was 2.5 meters, is basically optimal. The projectiles are unable to break the sound barrier with air due to the fact that the expansion speed of gas is limited by its compressibility. As the air expands to fill the barrel, it cools down, causing the speed of sound to drop. Eventually, the gas molecules can't move fast enough to exert pressure on the projectile, resulting in zero acceleration. When I had validated the model, I made the projectile for the large barrel. I 3D printed it out of TPU, and it weighs around 10 grams. For this test, I'll have to be careful regarding how much I pressurize it, because this one is gonna have a lot of energy.
3, 2, 1.
And of course I accidentally placed the chronograph the wrong way, meaning that I couldn't see how fast it was going. So I rotated it and decided to try again.
3, 2, 1. That one went fast.
This time, for some reason, the chronograph gave an error message. But it was going really fast, and the model predicted almost 200 meters per second or something at that pressure. I'll test this one more in a future video. So, I think this project was a success. I'm surprised that I was actually able to successfully model the system, and especially with an accuracy like this. In a future video, I'll do some more testing with some ballistic gel to see how powerful this thing is. I also started a co-fighting, so if you'd like to, you can support me on there to help me keep making these projects. Thanks for watching this video, consider liking it and subscribing if you haven't yet, and see you in the next one.